So last time we were discussing how for single mode fibers, like the fundamental LP01 mode, a convenient approximation is this Gaussian profile, right? And how we can use that, for example, to estimate splice loss, etc. So practically, like, how do we actually measure this spot size, right? Of course, you design the fiber and then manufacture it according to this theory we studied. We can sort of design it to have a particular spot size, but practically, like, after the fiber is made, how do you make sure that the spot size of the mode in the fiber is what you want, or like how do you measure it, right? So basically, how we can do it is just by letting the beam diffract, right? So let the light come out of one end of the fiber and then just let it diffract in free space, and then look at how the field profile looks like in some far field. Okay? So or equivalently the mode field diameter, right? So basically what we do is so we have some mode profile here, right? And we want to estimate what is the spot size of this, or the mode field diameter, right? So let's just say there's some fiber, and so just let the light come out, and then you know that as it propagates in free space, it will diffract out, right? And so in some far field, so right after some distance d, right? So this d is much larger than any of the other scales in the problem, right? So W or A or size of the fiber, right? Wavelength. So for example, all these scales are typically in micron scale, right? So this d would be like, let's say, centimeters. And so basically what we'll get here will also look like a Gaussian spot. Of course, the spot will be much bigger than what it is here. But knowing our distance from the fiber facet and then measuring this far field pattern here, we can estimate basically, or we can back calculate what is the mode field diameter of the mode. Okay. So if we take any point here, so again, like if you look at the field profile here, let's call this x and y axis. So again, the field profile will, or the intensity profile will look like Gaussian, right, along any axis. And so if we take some spot point here, right, so it will subtend some angle theta at the fiber facet output. Right? So we know this distance of the screen from the fiber facet, and we are looking at some distance, so y here, right? So this theta is roughly y over d, right, in radius. So, and I mean, this could be any r, right? Any point along the circle will subtend the same angle, right? So we can calculate what this profile looks, right? So again, from your basic optics course, there's a diffraction integral. Given some field profile at some particular location, you can calculate how the field profile will evolve on propagation. Right? So using the standard diffraction integral, So if you don't recall how this looks like, just look at the book. Right? You can calculate what is the intensity profile here in the far field. Right? So at any point here which subtends an angle theta, okay. So the mode profile looks sort of like a Gaussian function here, but in terms of sine theta. And now again, this d is very large. Other parameters are, so k0 is just 2 pi by lambda. Right? This w is the spot size that we want to measure. Okay, so you can see from here, by measuring the width of the intensity profile here in the far field, we can back calculate what w is. Right, so for d much larger than the wavelength or the spot size, right? So as I said, today these would be like centimeters. These are in micron. So we can approximate sine theta as theta, which is so r over d. Right, so r is the radial distance of the point. We are measuring the intensity here, right, from the center. Right, so this intensity profile basically I can write as right, so now this looks like Gaussian in the far field, right? E to the some constant minus r square by e to the minus r square by some constant square, right? So that constant square, that constant is basically the width. Right, so if we write this as some e to the minus 2r square by some far field spot size. So we put 2 here because again we are measuring the intensity, right? So in the field, if you assume the field to be e to the minus r square by w square, then the intensity square of that, so we have 2 here. Right, so this far field spot size, right? So that's the spot size here, right? Basically the distance from the center at which the intensity goes to 1 by e square of the center. So you can see that this far field spot size, right, depends on W, right? So you can see it's inversely proportional to the spot size in the fiber. Right, so this is the field diameter of the fiber. Half of that. So you can see actually if the fiber has, or if you have a fiber with a smaller spot size, you'll get a bigger spot in the far field, right? And if you have another fiber which has a larger mode field diameter, then the spot in the far field will be smaller. It's inversely proportional. Right, and again, that is coming from, if you go back to your diffraction basics, right? The smaller the spot you start with, that means by Fourier transform relations, right? It has more k vectors in the transverse direction. Right? So which means it will spread more. A larger spot size means that you have smaller magnitudes of k vectors in the transverse direction, so it doesn't split that, right? And specifically, basically, what diffraction, far field diffraction does is basically it takes a Fourier transform of your starting field profile, right? So if you have some field profile here, after diffraction over a long distance, basically the profile you get is the Fourier transform of the starting profile. So since here we are starting the Gaussian profile, the Fourier transform of a Gaussian is Gaussian. So here also we have a Gaussian, except because of the Fourier transform, the spot size is now inversely proportional to the beginning spot size. So basically, like you go from x to k, right? 1 over. Right. So if you plot this, again it looks like Gaussian, right? So, for example, with this angle subtended, you plot this. This looks like that. So this, let's say, is for a particular spot size. So this is, let's say, for mode field diameter 8 times the wavelength. If I go to a different fiber which has double the spot size, right, then the far field pattern now is narrow. Okay. So basically the point at which this goes down by so this goes down by 1 over e square here. This theta e angle here is given by, right, the angle subtended is the far field spot size divided by the distance of the screen from the fiber, right? And from here we know the expression for the far field spot size. So this is just, if you can write as okay. So we can see by plotting, by measuring this intensity distribution of far field and seeing where it goes down to, where the intensity goes down to 1 over e square of the maximum, we can relate that angle to the spot size at a given wavelength. Okay, so this way we can measure the spot size in any given fiber experimentally. So one thing to note is that, again, this is under the Gaussian approximation, right, which as we saw last time works quite well, but there are some small differences that show up when you take the actual Bessel function profile, right? So for a step index fiber, the lowest order mode is actually Bessel J0, right, and then K0 here in the cladding. So if we actually calculate the diffraction pattern obtained by Bessel, like starting from a Bessel function here, okay, then basically you notice some differences in the sort of for large angles here, or for large distances from the center, right? So near the maximum in the middle, it almost looks like a Gaussian. It's well approximated by a Gaussian, but then you get these side lobes, okay, which is not captured. So like the Gaussian will look like this, right? But due to this Bessel function, right, you actually get like certain minimas at certain places. Okay, so you get these side lobes, which is not captured by the Gaussian approximation, right? And turns out that if you do the actual diffraction integral with the Bessel functions by the position of these minima here, right? So at what particular locations these minima are occurring, you can sort of back calculate from that and obtain what the V number of the fiber is. Okay, so if you, for example, go to a different fiber with a different V number, then this profile sort of looks, it shifts. Okay, so the position of the minima shift for a different V. So again, if you're more interested in what these exact numbers are, how to get the V number from these values, you can, there's a discussion in the book, you can take a look at. But we won't go into that. This Gaussian approximation, as I said, works mostly quite well, right? So we know the wavelength we are working at, and from this we can get the mode field diameter, right? And from that, right, we can get, for example, the core size of the fiber. Okay. And I think so. There are experiments like this that you can actually do in the fiber optics lab here. So hopefully, if next semester you guys are allowed back on campus and you can actually do the lab course here physically, then you would be able to do experiments like this. So another important metric that we haven't discussed so far for single mode fibers or fibers in general is basically bending. So what happens if so far all our analysis has assumed that this fiber is always straight, right? It's always pointing straight. But of course, you know that practically that's not possible, right? So especially over long distances, there will be bends in the fiber, and in many cases you would actually want to bend the fiber, right, for practical ease of use and to route it in different directions, right? So there will be bends in the fiber, and so does that have any effect? Right, so what we'll see is actually bending always results in a loss, which a priori may not be very obvious, right? Because we have this guided mode in the fiber, and you would think that, okay, like anywhere the mode is being guided, right? For example, the power is confined in the core, and so in the ray picture, like total internal reflection is taking place. In the wave picture, we have this confined mode in the core, which is propagating without any change. So why should bending matter, right? Like it's solely seeing the inside of the fiber, and wherever the fiber goes, the mode should just follow, right? But you think a little bit more about it, right? So for a straight fiber, which we've discussed so far, right? So we get some mode profile here. So the intensity profile here, right? And so we have some mode profile in the cross sectional. So again, let's say this is x, y, and Z is the propagation direction, right? So we have some mode profile, and then in the Z direction we have a phase, right? So basically what's happening is you have plane wavefronts here, right? So for a given Z, right, at a particular Z, the wavefront is plane, right, which means like all points at a particular Z have the same phase. So it's a plane wavefront, which basically is like going, right? Right. So the wavefront is this wavefront is moving at the phase velocity, right, which is C over the effective index for the mode, right, which is clearly told here, right, or this is basically omega over p. Right, so that's all fine. But now let's say I have a bend in the fiber, right? So fiber is bent, right? So there is some radius of curvature, so it's bent about some point, central point, right? So radius of curvature is some capital R. Right, so now what's happening? So if you look at the mode, right, so if you go back to this plane wavefronts here, so the wavefront is sort of in a direction perpendicular to propagation direction. Right, so now you look at these wavefronts, what's happening? Right, so here the propagation direction was perpendicular to the wavefront, right? So all points on the wavefront travel the same distance with the same time, right? So the entire mode is sort of propagating, and yeah, there is no issue. But here, you see what's happening. So the points on the wavefront, which is like on the inside, closer to the point about which the fiber is bending, right? So here you can see that this point has moved here, 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 here. Compared to if you look at a farther point along the wavefront here, like here, this has moved like that, right? So you can see this point has traveled a much larger distance than this point. Okay. So now, and you can see with distance basically it's acquiring a phase, right? And so and these are by definition wavefronts or phase fronts which all have the same phase, which means that if it has to maintain that same phase, right? This is traveling a longer distance, but it has to maintain the same phase, right? Which means what? It has to travel at a faster velocity, right? So the time interval that this point sees and this point sees has to be the same for the same phase to acquire, right? That can only happen if this point is traveling faster, right? But for a mode, like the entire mode is traveling together at some speed, right? So you can see here we have a contradiction, right? Like a mode by definition means that the entire wavefront is moving at the same speed, but if we have that condition, we can see whenever you have a bend, you cannot maintain this condition of all points on the wavefront having the same phase, right? Because so if all points are traveling at the same velocity, then this is traveling a longer distance, so it will acquire a larger phase. So now this won't remain a wavefront, plane wavefront anymore. Right? So you can see that this kind of mode cannot be supported in a bent fiber. Right? And not only that, right? Okay, so if we measure some distance from the center of the fiber here, right? So this is the center of the fiber, so this is A. So if you measure distance from the, so remember our coordinate system for solving this in the cylindrical coordinates. So radial distance is measured from the center of the fiber, right? So some r here, right? So if the distance here in the center traveled is some L naught, right? So I don't know how to denote that, but basically the distance traveled by a point which is at distance r from the center of the fiber, right? That goes up with r, basically, right? So L naught is the distance traveled by the point at the center of the fiber, right? As I increase my radial distance from the center of the fiber, that point on the wavefront has to travel a longer distance by this amount, right? So again, if we want to maintain the same phase, that means the phase velocity has to be also a function of distance, right? So phase velocity is given by C over the refractive index or the effective index in this case for the mode. So you can see that the effective index has to scale like this. Right. So, but if that has to happen, we know that, so we have a core index N1, cladding index N2, right? Which is also the case here, right? And we know for guided modes, N effective has to be greater than N2 and less than N1. But if you want to satisfy this, like there will be some critical point here. So at some critical distance here, this N effective will become equal to N2, right? Because with increasing R, the N effective is going down. So you start from 0 at the center where N effective is somewhere in between N1 and N2. As you go out, the N effective has to decrease. So at some distance here, it will become equal to N2, and then beyond that, right? Basically, it will fall below N2. And we know that if the effective index of the mode is below the cladding index, that is not a guided mode anymore, right? So this means that you can call it a radiation mode, right? Or basically, the power is radiated away, right? There is no, right? So once you go beyond this critical distance, right, that power from this condition you can see cannot be guided, right? So that has to that will leak away into the cladding and basically, yeah, right? So by this argument, we can see that there will always be loss whenever you have a bend. Right? So, in other words, there is no truly guided mode for a bent fiber. Okay? Because, again, from this sort of physical heuristic arguments we made, right? There's no way to maintain a wavefront, like constant phase wavefront, right? And even if there was some funky way to do this, to have like a effective index depending on position, even then beyond some critical position, the effective index will have to go below the cladding index, which means it cannot be a guided mode. Yeah, so this is clear that, right? So the distance right? So if this distance is L naught, right? So now I go some distance r away from the center. So the distance that this point has to travel is given by this, right? So the angle separated is the same. So this distance you can see will be L naught, right? Where r is the radius of curvature. Okay, this is clear? Right, basically, so for this guy, the distance from the center is now r plus r. Right, so basically L naught divided by r will be this distance divided by r plus r. So you can see this distance has to be L naught plus r plus r, right? So again, so now this guy is, this point here has to travel a longer distance compared to this point, right? So if the effective index at this point is n effective of 0, right? So the speed here is c over n effective at 0. The speed here is c over n effective at this point, right? So basically for this, if you want to maintain the constant phase wavefront here, right? So let's say we started from a constant phase wavefront here, all these points had the same phase. After traveling to here, if all these points also need to have the same phase, right? Because the only way that is possible is if the time right, both these points travel to here in the same time, right? So basically distance by speed for both of these have to be the same, right? So L naught by c by n effective at 0 has to be equal to L naught times 1 plus r by r times c over n effective at r, right? So yeah, from here then we get this. Is that clear? Okay. Right. Yeah. So you can see that after some particular distance here, the effective index will go down below the cladding, and when that happens, basically you can say we don't have a guided mode. Okay. And this will happen no matter what. You can see, as soon as this capital R is finite, you will have some critical distance that this will happen at. So any bend in the fiber means that you no longer have a guided mode, and power is radiated away, which means you have loss, right? So that's called bending loss, right? So whenever there is a bend in the fiber, you get some loss due to this phenomenon, right? That cannot have a guided mode anymore. So basically how this is modeled is that, so again, sort of coming from this point, right, that points farther away have to right, have an index which goes like that, right? So what you can do is model a bent fiber by an equivalent straight fiber, okay? Except instead of having constant indices here, we have an index variation something like this, okay? So now imagine a straight waveguide where, or straight fiber with Okay, refractive index profile like that. Right now, R phi are again now in the cross-sectional plane of the fiber. So now imagine we are looking at a fiber which is like going into the board. Okay. So it's a straight fiber, no bend, going into the board. Okay. And so we are modeling a bent fiber, right? So let's say, it's bent about this point. So this is R, right? So the bend is going into the board, right? Like that. So that bent fiber can be equivalently modeled like a straight fiber, okay? But not with constant indices now, but with a graded index profile like that, right? So where R, again, R and phi are the same R and phi, so, right? So any point here, so that's R, and this is phi. Right, so why do we take profile like this? So you can see, so for phi equal to 0, cosine phi is 1. So along the direction of the radius of curvature of the bend, right? You can see, so this will look like now n1 times 1 plus r by r. Right, so along this direction, it will have this 1 plus r by r profile. Okay, so and if you take, so imagine now phi equal to 90 degree, right? So now that's a plane which is perpendicular to the radius of curvature here, right? So so points along this, they're all traveling the same distance, right? So on this plane, because it's bending into the board, all these points are traveling the same distance. Unlike for this axis here, all these points are traveling different distances, right? So that's why we, so for phi equal to 0, we get a 1 plus r by r profile here. But for perpendicular, cosine phi is 0, so it's just n1 all along here, right? Because all for points here, it's like the bend makes no difference because all of them anyway are now traveling the same distance, right? Because they're all the same distance r from the bend. Right, so I hope this profile is clear. Right, why we take it. And any intermediate point here will have, right, will travel a longer distance by this cosine phi. Right, so basically this directly is coming from here. So here, when we were looking like this in a 2D plane, we were basically looking at this phi equal to 0 plane. So we could go to phi non-zero planes, right? So that will be like going up a little bit here. Okay, so then we'll have this extra cosine phi. Okay, is that clear? Right, so that's the fiber radius. Core radius. Okay, so bent fiber basically is modeled like a straight fiber because we know how to solve for modes in a straight fiber. Right? In a bent fiber, basically what is happening is now the z direction, the propagation direction is not fixed, right? So that's why it becomes, you can't solve for really modes. And from the argument we just had, basically anyway we showed that there cannot be any guided modes. Any mode will only be a radiation mode. So now, right, basically you can solve for the modes So again, so how does this this gradient index profile look? Right. So if I take again, like let's say if I go along this axis, I can call that the x direction, for example. Right? Y and z is into the board. Right. So if I didn't have any bend, right? So the straight fiber, the refractive index profile looks like that, right? So N1, N2. So this is the core, right? Right. So this is the straight fiber. Right. And this is what we solve for modes in, right? So now when we put a bend, basically we are saying that we can look at that as a straight fiber again, but now the refractive index profile is like this, right? So now if you put phi equal to 0 along this plane, you can see it will look like this. Right? So as I am going towards larger x, my refractive index is increasing in a linear fashion. Okay, so at the center it's still, so here it's still N1. Okay. So now basically, to see the effect of the bend, we need to solve for modes in such a refractive index profile. Okay. So now you can see this looks like a weird profile, right? Because so this index here keeps going up, right? So for example, in the straight fiber, we solve for a mode, we get some n effective, which is typically somewhere here between N1 and N2, right? So if we take that same n effective, right? So again, let's say this is N2. So the n effective, let's say, will lie somewhere here, right? So you can see that. I should make this a bit bigger. Okay, so if I take this n effective here, the same n effective, you can see at some distance here, it will now go below the cladding, effective cladding index. Okay, so beyond here, so if you have some mode profile like this, right? So here the mode profile looks like that, and it's guided, right? But now here, as soon as we have a bend, right? So here, after the point where n effective becomes lower than the effective cladding index, for this part, right? Now we are in sort of the radiation zone. Okay, so you can see that this part of the power has to be radiated away, right? So fraction of the power will keep losing as the mode propagates. Okay, so this is not a proper mode, right? It's what is known as a leaky mode, right? Which means that basically now your propagation constant, instead of being a real number, has an imaginary component. So which gives basically a loss, right? So this part of the power being radiated away is giving me an imaginary part of the N2. Yeah, so here N2 would be again here, right? So at the center, right? Again, here at the center we have N1 and N2. So this delta is what is the fibers delta. Okay, so yeah, so this will be in the core, right? So and in the cladding, basically I replace N1 by N2. Okay. Right, so this fact that we talked about, that a bend cannot maintain a constant phase wavefront, which means there is no guided mode and power has to be lost, right, is captured by this kind of refractive index profile, where basically the effective index will become smaller than the effective cladding index because it keeps going up, right? At some point, it will become more than the ineffective we had from the state file. Right, and basically the part of the mode which is extending beyond that region is lost, basically. So, right, so basically there's a just like we have a theory for actual guided modes in a structure, right? There's a theory for leaky modes in a structure where basically you don't have well-defined guided modes, right? But you can sort of do a similar analysis that we had, like solve for the wave equation, but now assume like the mode is not properly guided but has a loss coefficient. So, so we won't go into the details of that. Again, if you are interested more, you can look at the books. And I posted the relevant section. So, if you want to go into the details of the theory of how to calculate these leaky modes, right? But basically the point is that, yeah, so you take this kind of refractive index profile, then you calculate the leaky mode, and then you find out what the imaginary part of the propagation constant is, which gives you the loss factor. Right, so you can see for this kind of refractive index profile, there cannot be a well-defined guided mode because, right, the cladding index keeps going up. So there is no, you cannot have confinement because you cannot satisfy this condition for all points in space. Okay, so basically because of this imaginary part, basically what happens is as the power is propagating, right, you get a loss like this, right? Because here, like if you have an imaginary part, you'll see that this will give me e to the minus alpha z. Right, so the power is decaying with distance, and there's a loss coefficient here, right? So this bend loss coefficient alpha b, you can calculate by this theory of leaky modes, right? And so it's quite complicated. So we'll just sort of look at the form of the final result here. And there are like a couple of different ways of doing it because again this is an approximate theory, leaky modes. So there are 2-3 different methods that people can use. But sort of like the form you get for the bend loss looks something like this. Okay, so it looks quite complicated, but again, so this U and W are the usual U and W we had, right? So U is kappa A is K0 A n1 square minus n effective square, right? So now this n effective is the one is the n effective for the mode in the straight wavelength. So for the straight fiber, we know what the modes are, we know what the n effective is, right? And then we bend the fiber, we want to know what the loss coefficient is. So basically, we put the parameters that we have for the straight fiber. Okay. This W is gamma A. Okay, V is same V number. Okay, so basically the thing to note is sort of how it scales with the bend radius R, right? So a tighter bend would mean a smaller R. Right? So you can see that it goes as R to the minus half, some e to the minus constant times R, right? So as the bend radius decreases, which means the tighter bend, right? You can see that the bending loss increases quite a bit, right? Exponentially. And then this constant here, you can see we have fiber parameters here, right? So for example, this A, you can see here, it has the size of the core here, right? So this A is proportional to, for example, 1 over A cube, right? So you can see that, for example, so from here, if you have a fiber, so for a given R, or a given bend radius, the loss coefficient goes up with a smaller core, right? Okay. And finally, there's also a dependence on, so this U and V depend on the index difference, right? So delta, basically, right? So this is, you remember square root of 2 delta. So the dependence on delta is that, so again, the bending loss goes up with decreasing index contrast. So you can see that these are actually significant for single mode fibers, right? So for single mode fibers, for example, step index, we want B less than 2.4, which means that the core size and the index difference here have to be small, right? They can't be, we can't just make them larger and larger, because this B number has to be smaller than a particular number, right? But we see here the bending loss actually goes up with smaller delta and also smaller core radius. Okay, so for single mode fibers, you have to be careful of this bending loss. Okay, so this, yeah, so it's a loss, right? E to the minus alpha z. So this has units of per length. So again, if you take the dB of this, you can quote the loss in dB per length, right? dB per meter or dB per kilometer, right? We do for propagation loss. So if you look at a typical variation, so we have bend rate curvature of the bend on the x-axis, right? So how tightly we bend it. This is in millimeter. And on the y-axis we have the bend loss in dB per meter. So both are in log scale. So we take a particular fiber with some parameters here. So like typical, let's say single mode fiber parameters. So N1 1.46. Let's say core size about 5.5 micron. Wavelength of operation 1.3 micron. Okay, and then we vary this index difference here, delta. Then for each index difference, we'll get a particular curve, right? So as the bend radius increases, the loss goes down, right? Basically, also that's intuitively obvious, right? Because a larger and larger, so R tends to infinity means no bend, right? So this looks something like this, right? So this curve is very steep. It falls over orders of magnitude by small changes in R, right? Again, because the dependence here isn't exponential. So as delta, so this is delta 0.005, 0.004. Okay, so as delta, so for a particular bend radius, as delta goes down, the loss increases. Right, so to give you some idea here, so for delta equal to 0.003 for these parameters, you have V about 2.4. Okay, so if you want to be single mode at this wavelength, your delta has to be 0.003 or lower, right? So you need to be in this region. Okay, so you can see you can have significant bending loss. So this is a bend radius of 1 centimeter, right? So you have very high bend loss. So to make the bend loss negligible, you need to go beyond here, right? So like few centimeters or say 10 centimeters and beyond. Okay. So as a rule of okay, so basically the take-home message is that you can't keep bend the fiber very tightly, right? Because that gives you very high loss. So whenever we want to change the direction of the propagation of the fiber, the bend have to be over like large bend radius. So like smoothly you have to. So typically, few centimeters bend radius at least you need to have. So many times, for example, we also use fiber spools where basically the fiber is wound around like this plastic spool, and you basically wind the fiber around many times. So you have like let's say kilometer length of fiber in just a small form factor, right? So then also the spool size, the size of the radius of the spool around which you bend the fiber has to be minimum, right? So typically it's kept like 10 centimeters or more.